Today we're going to have a look at how we can prove the fundamental theorem of calculus. Now, the syllabus dot point for the advanced course says that you need to be able to understand and use the fundamental theorem, and this is the theorem that it states, and illustrate its proof geometrically. So that's what we're going to do in this video. Now, examining this proof here, the two notations at the end are sort of familiar. Remember when we first learnt to differentiate, and we differentiated little f of x, we said that if we differentiate it, then we're going to call it f dash x, among other things. We also use dy dx and some other notations. And if we do the opposite of differentiating, which we've now defined as integrating, then that will take us back. So then the question was, well, what happens if you integrate little f of x? What do you get? And the notation that we used was big f of x, where the big F denoted that it was the primitive of little f of x. So it stands to reason that if we integrate going this way, then if we differentiate this one, we will get back. Now, that leads us to another piece of notation that we could use for little f of x. If we differentiate something by adding this little dash, and that's the notation we use to show that it's been differentiated, then to me it makes sense that we could be able to differentiate this. We could give it another name, an alternate name, and we could call it big F dash x. And these two notations would effectively mean the same thing. Does that make sense? So here we've got one of these notations in one side and the other in the other side. So we're showing that they're equal. And what we're saying is that if we ddx, or if we differentiate this section here, then it will equal either of these. Now, what does this part here mean? Well, we've defined this, and let's look at what I've written here in red now. So far, we've just defined big F of x as the area underneath a curve. Now, the way that we did that, remember, as we said, if we look at some curve, let's call it y equals f of x, and we define some area underneath it between some bounds, let's call them a and b, then this area in here that's trapped by x equals a, x equals b, the x-axis, and our curve, we defined that as big F of x. And to find it, remember we reasoned that if we made a whole lot of little rectangles and added up the areas of them, it would be very, very close. As long as the rectangles were infinitely thin, it would be very close to our area. Now, to find the area of a rectangle, we do base times height. And remember, for each of these, we said that the base would be a tiny, tiny change in x. And that's where the dx part came from, a delta change in x, which was simplified to dx. But we also said that the height of each rectangle would actually just be f of x. Now, what did we do with these base times heights, these areas of all of these tiny, tiny, very skinny rectangles? We added them together, and the notation said, let's sum them together. This is a stylized S, and we'll add them all up from when x is the bottom number, A, all the way to when it's the top number. Now, this looks a little bit different from this and this. Why is that? Well, we've seen that we want to be able to move this upper bound so that we can say, hey, let's find the area underneath this curve between the lower bound and, let's see, something that I can move or change. So if we want to be able to sub in a movable upper bound, it makes sense then to sub in not b, but x, and say that let's make x, let's write here a disclaimer, where x is in between a and b, and we need to say where this curve is continuous, because we know if it's not continuous, then we can't find the area underneath it. So we've got a few little disclaimers there. We've defined x as being somewhere in between a and b, and we've said, hey, instead of going area from a all the way up to b, let's just go up to x. Now, a little problem happens, well, it's not really a problem, but when we make those square brackets and we sub our upper bound x in to a formula that's already got x's in it, some people think it looks a bit clunky to sub x in where there's already an x. And that's where this f of t dt has come about. They've said, look, let's call this y equals f of t. We'll make this be the t-axis going all the way along here, not the x-axis. And that way, if we integrate, or if we find f of t dt, then the part in our square brackets will have t's in it instead of x's. And that way, when we sub an x in, it won't look so clunky, it'll look a bit more logical. So, let's go back a step again. We've defined big F of x as being the area underneath the curve. That's what that notation means. It means sum up all of the areas of all those little rectangles between here and here. Okay, so it's the area under the curve between the upper and lower bounds, this and a and x, and the x-axis. So that's all we know of big F of x at that stage. It's an area. Okay, but let's have a look at this part in blue. We've also learnt to integrate algebraically by finding the primitive. In other words, we've said, what function could I imagine that when I differentiate it, I'd get this? And so we've defined the primitive of little f of x as big F of x. We've said if we integrate this, we'll get something, let's call it big F of x. Well, what we're here to prove today is that this big F of x is both things. It's algebraically, it's the primitive of little f of x, and it's also that area under the curve. We're proving that those two things are the same. Now, if we want to prove that integrating little f of x actually gives us big F of x, where big F of x is an area under the curve, it's really hard to prove integration. So what we're going to do is work backwards. If we can prove that differentiating this gives us this, then we'll automatically have proved that integrating this one gives us this one. So what we're going to do is we're going to prove that differentiating big F of x, which is differentiating all of this, in other words, we're going to d dx, the area. Now, how do you differentiate an area? Well, we're going to use first principles and we're just going to work our way through it. We're going to prove that differentiating the area under the curve will actually give us little f of x. Now, when you differentiate by first principles, you use this formula. We've seen this a number of times already. F dash x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So that's the formula that we're going to use. Now, something else we also know, we've defined big F of x as this sum of areas underneath the curve, and we've got this notation to show it. And so it makes sense that if big F of little x is the area from the lower bound of a up to the upper bound of x underneath some curve, y equals f of t, then big F of x plus h, well, the only difference here is that the x has been replaced with x plus h. So clearly it just means that we're going to an upper bound of x plus h. So we can start by saying, if we differentiate by putting the dash in to big F of x, then what we're going to get is the limit as h approaches 0 of, well, compare these two formulas. The only real difference is that this one has a little f and this one has a big F. So clearly we can use the same formula and say we need big F of x plus h minus big F of x all over h. Or if we wanted to, we could write that using just this part here, and then instead of dividing by h, we could multiply by 1 over h. Now, why have I done that? Well, it's because I want to get this part here on its own so that I can use my understanding of what these terms really mean to change it a little bit and make it look different. Now, another thing I'm going to do at this point is use some colours to help me here. So let's change this to be written in green, big F of x plus h, and we'll make big F of x red. Okay, now let's look at what we can do to find a simpler expression for this part here. All right, well, we've defined these as areas underneath curves. So if we draw some curve, let's call it y equals f of t, and we're going from a lower bound of a, and this will tell us that the upper bound would be x plus h. Okay, so let's make that in green up here somewhere, and let's put our line in red somewhere here. Now let's call this x, and let's call this x plus h, where h is just a little bit bigger. And then we're going to basically take the limit as h gets smaller and smaller, and the green line is going to approach the red line. Okay, so let's think about what big F of x plus h means. It actually means this area here, which I'm going to outline in green, and let's colour it in a little bit as well, this green area here. So we need to take that green area and we need to subtract this area here, which I'll outline in red now. Let's shade it a little bit the other way. Okay, so can you see that if we take this whole green area and we take away the red area, what will we be left with? Well, we'll be left with this area here, won't we? Let's make it, what, blue? Okay. And in fact, let's use colours to say, let's put a circle around this whole bit to say that'll be the blue section, which I can now colour in blue. Okay, well, how big is this little blue area here? It's going to get smaller and smaller as h approaches 0, isn't it? Can we come up with some sort of formula for it? Well, when we first looked at summing up a heap of little rectangles with our whole idea of what the area under the curve could be found as, didn't we trap our areas between rectangles? We can do the same thing here. Now, if I extend this line up so that I've got an upper rectangle here, and then I extend this line straight across so that I've got a lower rectangle here, can you see that this blue area underneath the curve is going to be a little bit smaller than the big rectangle, but it's going to be a little bit bigger than the small rectangle, okay? So we could say then that this whole section here, let's just rewrite it, big F of x plus h minus big F of x, and we've defined that as this blue area. We can see that it's going to lie in between two things. It's going to lie in between the area of this big rectangle. Now, how wide is the big rectangle? It's h wide, isn't it? And how tall is it? Well, if this is x plus h, then this over here is the function of x plus h. So it's going to be the function of x plus h times h, okay? And what about the little rectangle? Well, it's also h wide, and how tall is it? Well, if this is x, it is f of x tall. So we can put that over here, f of x times h. Okay, so we've got now a little expression for how big this area is. Okay, next I'm going to change my notation a little bit. Here, haven't we said that this is one area minus another? We've got a notation for areas under the curves. We use this, don't we? So how about we tidy this up a little bit and say, let's call this the area. Now, it's from a lower bound of x to an upper bound of x plus h, and it's the area underneath this curve, y equals f of t, dt. So that whole part can be written more tidily like this. And then over here, we've got the same thing. We'll just repeat it again. Gee, it'd be nice to get rid of that h, wouldn't it? And this h. How about, at the same time here, we could divide this part by h, then it would be missing, because h divided by h is 1. Divide this part by h, so that it won't be here, and all we've got to do is divide this part by h. Now, dividing by h is the same as multiplying by 1 over h, so let's write that out the front. Now, dividing everything by h was a great idea just for tidying up the two outside parts of my equation. But the other thing I've done now, I've got 1 over h, and I've got this part here, which I've reasoned is equal to that. What I'm actually trying to generate here in the middle of my equation is something a lot like this, okay, so that I can come up with an expression for all of this. Now, I've got my 1 over h, it's here. I've got just new notation to express all of this part, and I got it by reasoning that these were areas and subtracting one from the other and coming up with a way of writing that. So now all that's missing between this and this is taking the limit as h approaches 0. So how about we go ahead and do that? Let's take the limit as h approaches 0 of 1 over h and our area from x to x plus h, f of t dt. Now, if I've taken the limit as this part approaches, as h approaches 0 in this part, I need to take the limit over here and over here. So I've taken the limit as h approaches 0 of everything there. And I've got some, in fact, I should have equal signs here as well. I know it needs to be greater than or less than or equal to. Now, in most cases where we're differentiating by first principles, we normally try and tidy this whole section up so that we don't have h in the denominator, because then if we can sub in 0, we can't do it when it's down here because you can't have 0 in the denominator, we can come up with what the limit is as h approaches 0. Now, this time we haven't done that. We've still got our h sitting on the denominator, and we can't really tidy this up anymore. But what we can do is we can say, well, what's the limit of f of x as h approaches 0? Well, f of x doesn't have any h's in it, so it will actually just be f of x. And what's the limit as h approaches 0 of the function of x plus h? Well, if h is approaching 0, then this line is getting to be virtually on top of the other line. We're going to just have here f of x, okay? Because if we're adding x plus 0, we've got just x there in the brackets. So what we've done now is that we've actually found that all of this, and we've defined all of this earlier on, up here as being big F dash x, we've found that it must lie between f of x and f of x. So we've sort of sandwiched it in between two things that are identical to each other. So therefore, big F dash x must equal little f of x, because how can it be smaller than or equal to this one and greater than or equal to this one if they're both the same? It must equal it. And then we've finally proved the fundamental theorem, which is that if we differentiate big f of x to get little f of x, then if we integrate little f of x, we must get big f of x.